Hey guys, this is me, Mr. Wee. I'm here to continue off of where we left off for notes um, from our previous class. So last time we left off at me giving you a list of the actual derivatives of both exponential and logarithmic functions. So the first one is like a when you have x variable as an exponent. So this is an exponential function where your base is e, natural log. Or I'm sorry, not natural log, but just base e to the power of. And then you have this here. If you have a derivative of something else that's not necessarily with the base of e, but still has an exponent to the power of a variable. And please note that a has to be greater than 0. If you think about that, that makes sense, because if it was 0, then 0 to any exponent wouldn't really matter. It would just be equal to 0. And also, you don't want x just to be 1, so x cannot be 1. So please go back in your notes and kind of modify that if you took that on when you were with me on Wednesday. That a just can't be equal to 1, because 1 to the power of anything, if you think about it, is just 1. So this derivative doesn't really apply to these two situations here. Okay, or I'm sorry, it applies to this and it does apply to this. So we just can't have a situation where a is equal to 1 or a is equal to 0 if you think about it. Okay. So this is what it would be equal to. A is just any constant, and with those two parameters, it has to be greater than 0 and not equal to 1. And then this is the formula. And then here's the formula of the natural log of x. The natural log. So this is just the formula here. Hopefully you wrote that down. And then the derivative of log base a, some kind of constant, to something that's differentiable. You could put the x in there essentially, but that's so hopefully you can write this down. This is going to be a quick summary sheet while I go through some examples for each of these, for each one basically, for each of these scenarios. And just let me go over this really quick. I'm not going to go over a proof, but basically right now the way I'm going to handle this is I'm going to give you guys the formulas, and they're just going to be memorized at this point. Okay, functionally, you just need to memorize that the derivative of e to the x is just e to the x, and the derivative of au, like some kind of constant number to some kind of a differentiable exponent, is this guy right here. You're gonna have to memorize these, but if you want to know why why it comes out to be like this, your book actually shows you proofs for why this happens. So let's see. So for example here, the derivative of a to the x, the a to the x, which is right here, a to the x, this should be the proof, the mathematical proof, if you want to go back and you actually want to reread why it is this. It's not just completely made up. Okay, it actually had to be mathematically proven through a few steps. There are also videos on doing this too. So it's really easy. You just go on YouTube and then you just you search the key term proof, and then you put derivative of whatever it is, a. So how I would do that is let's just go online and check that out and see what that would look like. So again, let's kind of move this over here to this side. Derivative, proof of derivative. So there's this one here, or the first one. So look on the left-hand side of your screen. So for this derivative here, the reason why the derivative e to the x is just e to the x, well, go back on the right side of your screen here, as I'm kind of showing you. You could pick any of these videos and it'll actually show you why it comes out to be this way. Okay, last year I spent a lot of time just doing proofs in the class, but realistically on your exam, you're not going to be asked to actually prove any of these proofs. You're just going to be given a bunch of problems where you have to plug it into the formula that you have to end up memorizing anyways. But for those that cannot just take this at face value and would like a proof, I would suggest you do this. Okay, so Just some keynotes. So look at where I highlighted where it says derivative of e to the power of x. Just a reminder, this is a caret sign. So on your keyboard, it should be you would hold the shift key and then you'd hit the number 6. That's to the power of, and you can put like 6 or 7, but really you want a variable, e to the x, okay? So you can find proofs for each of these derivatives. They're actually really cool. In college, though, you could definitely, I would definitely say that if you're going to be more of a mathematical or even physics based or more quantitative numbers sort of major, I would highly recommend that you actually go through these proofs so you actually see the beauty in where these formulas come from. Okay. Um, One other beautiful thing too, this one's probably the easiest one to prove without having to do math, like to prove the actual formula. Um, like, let's see, let me see, derivative graph of x squared. So let's see if they have Google images here. This is kind of weird, but if you remember having to draw derivative graphs, like if your function was a parabola, right? So just look at on the left-hand side, or like up here where I'm kind of moving my cursor. If your function or your original equation was a parabola, if you had to draw the slope for that, these slopes at each of these individual points are negative, so they're all on the negative. Here at this flat spot is where it's 0. So if you drew a derivative graph, right, and it, at the for this parabola here, it would be represented as a whole bunch of negative slopes. Then it hits 0, and then all the slopes become positive, right? So that's what this would look like for the derivative graph, and then the original graph would look like this. What's interesting is if you actually try to draw the derivative graph of e to the x, okay, so here's e to the x, just e to the x normally, right? Oh, and in this blue one here, this is e to the negative x, and red, this is e to the power x. Watch what happens when I look up for the derivative. The derivative of e to the x, and then you could just put graph. If you try drawing this, it's gonna be really funny. I don't. Okay, actually, yeah. What it's basically saying is, if you drew the actual graph for e to the x, you're gonna get the same exact thing, e to the x. It's really ridiculous to think about, but you can prove it to yourself. Try drawing a graph for e to the x and then draw the derivatives for each of those points, and you're going to see it's exactly the same thing. In fact, that's what makes e so weird. E is a natural base, and the natural log, right? Natural log ln is log of a base e. The reason why e is so significant is because it has that one property. If you look in a lot of textbooks, it says that e is that one weird base where if you draw the derivative graph of e to the x, it would look exactly the same as just the original function e to the x. I guarantee it. So just try it out. We're not going to spend time to do that, but this is the one weird scenario where the derivative of the function looks exactly like the original function. The derivative of this is e to the x, which looks exactly like the original function. Okay, so anyways, after talking about proofs, and I didn't actually show any proofs, but I did tell you what they are, kind of, and where to find them, let's actually get into some problems, okay? Okay, so, whoops. Let's see if I still have my... All right. So we got 4 different problems that we kind of got to talk about. Let's find let's do the derivative of e to the x power, and then the example would be find dy dx if y was equal to e to the x plus x squared in parentheses. So let's take a look at your notes. This is what you have so far. If your derivative e to the x was equal, if it was e to the x, it would just be e to the x. But we have something that looks more like this, e to the u. And the reason why is because u, if you exchange it here, what it says is the derivative of e to the u is e to the u, like normal, but if by the chain rule, if u is differentiable, you have to take the derivative of the inside function, or u, du x. So first, how you take care of this problem is to define what your u is. My u is right there, so it's going to be this whole thing, x plus x squared. And I would like to know what du, so step one is to establish what your u is. Du over dx is, what's the derivative of x plus x squared with respect to the fact that x is your independent variable? That should be 1, and then this should be 2x, okay? Let's keep that in mind, and then we know, it says right here, that the derivative of e to the u is equal to eu times du over dx. So let's do that. The derivative, let's say the derivative of, you could say y if you want, because technically you are dealing with a y equation. Derivative of y is equal to, or you know what? Let's just do, let's keep with the formula. D of dx times e to the u is going to be e to the u, right? This is based off of your formula that you just went off of right here, times du over dx. That's it. It's as simple as that. And then you just substitute in what your original u and your dux, or your du over dx is. Du, or u, I'm sorry, is x plus x squared. So you write in x plus x squared times du over dx. Well, we established that as 1 plus 2x. That's it. That's all you had to do. Simple as that. Okay. So this is equivalent to dy over dx. Just letting you know, okay? Because this is what y was equal to. Dy over dx is equal to this. So the derivative of this whole guy is equal to dy over dx, and is essentially equal to all of this. Okay. All right. So let's find a example for the derivative. If you have any questions, or you're having any troubles learning this, please come in and talk to me, and I can help you out. The derivative a to the x, okay, or some kind of constant times the power of x. Let's have an example here. The example asks, at what point xy on the graph of the function, sorry, that does say function. It looks really weird, but that's just function. I know it's really hard. Y is equal to 2 to the power of x minus 3. Does the tangent line have a slope of 21? Okay. For one, what the heck does slope mean? That means derivative. So the slope of this equation. So this is asking for dy over dx, okay? And it's asking for when dy over dx is equal to 21, okay? All right, and then we're looking for a point. Okay, so we're actually solving for x and technically y after we establish what our dy over dx is, and we know it's equal to 21. So let's find dy over dx of this guy. So if, again, y was equal to 2x squared minus 3x, what is this? What is the derivative of this guy? Okay, so let's see how we would take care of this. If you remember back, okay, so it looks like this is an exponential function, right, that has a base that is not e. So we don't use the derivative e to the x, but we use this guy. It's really simple. Let's copy this equation down. So I would say the derivative of a to u, in this case, a is right there, and then to the power of u. This doesn't have anything. It's just a constant, so don't even worry that it's there. Don't be confused or scared that you can't plug in the -3 somewhere in here, okay, because it really doesn't matter, right? When you find the derivative of a constant, it's just going to be 0 anyways. And then the derivative of this, let's rewrite this, is a to the power of u times ln, that's weird, ln of a, okay, times du over dx. Okay, so let's establish a few things. Can we define, so I would say, I like doing the u's always first. So can we find an exponent here? What is u in this case? I would say that's equal to x, and then du over dx. What is the derivative of u with respect to x? Well, what is the derivative of that guy, basically? What is, since u is equal to x, what is the derivative of that? That is 1, okay? And then one more thing is, what is your a? In this formula specifically, it looks like it's 2. Okay, so let's plug all this in. So we found that the derivative of a to the u is equal to all this. Let's plug in 1, 2, 3, these three things into this equation. Okay, so again, d, the derivative of a to the power of u with respect to x is going to be equal to a to the power of u, so that's 2 to the power of u, which is x, times, I'm substituting in all the values in for the appropriate letters, times ln of a, which is 2, times du over dx, which is just 1. So you have 2 to the power of x times ln of 2. Okay, but remember, it's asking for when the slope is equal to 21, and specifically at what point on our graph. So if you wanted to understand what was really happening, you don't have to draw this, but this is the graph. Okay, this is a graph, and you have a weird exponential function. I don't know, right there. Okay, and at some point, the slope is going to be equal to the slope that is, let's see, tangent, this tangent line that touches this what is it, this function of y is equal to 2 to the power of x minus 3. This curve right here at some point will have a slope. The slope, that individual point, is going to be equal to 21. Okay, it's going to be equal to 21. So we have to find the equation. Let's see, the equation for the slope, which we just did. It's 2x ln of 2, and we want to know exactly at what coordinate that slope is equal. Slope is equal to 21. We want to know the actual x, y coordinate. And how do you do that? Well, let's set this equal to 21. So step 3 is technically going to be equal to, set this equal to 21. And let's just solve for x. And whatever I find out for x is really what the x value is going to be for this coordinate where the slope is equal to 21. So I would divide both sides by ln of 2. That is an actual number. So let's cancel that. Ln of 2. I guess at this point you can rewrite this as 2x, 2 to the power of x is equal to 21 over ln of 2, which if you plug that into your calculator, that will be an actual, that will be an actual, that will have an actual answer. Let's see. Oops. And do I need to worry about anything else? Sorry about this, guys. I'm just kind of taking my time here. Let's see, did I need to bring up anything else? I think I did before I... Yeah, I think this is a... Okay, so let's go on. Let's continue our problem over here. 2 to the power of x is equal to 21 over ln of 2. Okay. So one strategy is, if you... the x is in the exponent. If you want to get it down, what you can do is you could take the natural log of this guy, and whatever you do to one side, you got to do the other side. Okay, natural log of this whole thing over here. And what ends up happening is there's a law, or there's a rule in logarithms and natural logs, that if you take the natural log of a base that has a power, the power comes down to the front. So you have x is equal to ln of 2, just 2 now, which is equal to the natural log of 21. And there's another rule here which says that if you do the natural log of a fraction, it's like saying the natural log of 21 minus, or the numerator minus the natural log of the denominator. Isn't that a crazy one? And then one more thing is, we want to get x by itself. And this looks really scary, so that tells you do have to study for your you do have to study over like the rule of logs, like various rule of logarithms and natural logs. Okay, and you have this weird scenario of x equals ln of 21 minus ln of 2 divided by the ln of 2. And I guarantee you, if you plug in any of these numbers or values or expressions into your calculator, you should get an answer. Okay, and these are actual constant numbers. These are not variables. So at the very end, you should get approximately, I'm going to say approximately 4.921. Okay, so that's the x value, but remember, I did ask for a point. So to find the point, let's go back to the very original problem here. Remember, I'm trying to find the point on the original graph. The original graph has the equation of y is equal to 2x minus 3. Even though I use the slope, which is the dy over dx, the derivative of this guy, and I set him equal to 21. So the derivative of this guy was, what is it? 2x times ln of 2. I set that equal to 21 to find what my x value was going to be. But remember, the coordinate, it's still going to be on this specific line, which is y is equal to 2 to the power of x minus 3. We have the x coordinate of, I believe that's 4.921. We have to plug this back into the original equation to find the coordinate of that point. Okay, so y again was equal to 2 to the power of x. So let's see. Step 3, step 4, we're going to say is to plug it back in, this x value here. And this is minus 3, so you do y is equal to the 2 to the power 4.921 minus 3. You put that in the calculator, and then I believe you approximately get about 27.3. Okay, so your coordinate is 4.921, comma 27.3. You just round up to like the first two numbers, three numbers, first number, doesn't really matter. First tens place, hundreds place, or thousands place, that doesn't really matter to me. Okay, so that point, again, that point where the slope is equal to 21 is going to be, we just found out, 4.921, comma 27.3. Okay, very good. So that's another example. Okay, let's see. Then we have two more examples to go through. We have an example for the derivative of ln x. And again, just to reiterate, that's d over dx, or the derivative with respect to x of ln of u of ln of u. Sorry, the derivative of ln of u is equal to 1 divided by u times du over dx. So that doesn't seem too bad. So, sorry about that. Might be really loud on the... Oops, that's not for us. Okay, so let's see. All right, so we have two scenarios here. Let's do example of the find dy with respect to x, or the derivative of y with respect to x, when your y is equal to ln of x squared. Not too bad. Okay, again, we see that original general problem. Let's figure out a few things. What are we going to assign as u? Ln of u, that's x squared. Ln of x squared, so x squared is going to be u. And if you take the derivative of u, which is x squared, with respect to x, that should be equal to 2x. So it's fairly simple. Now you just plug it into the formula. The derivative of ln u, the derivative of specifically, the natural log of u would be equal to 1 over u. So let's substitute in u. U is x squared, or u is x squared, times the derivative of u with respect to x, which we found to be 2x. Let's plug that in. That's 2x over x squared, right? And then we can cancel out one order of magnitude of x up here and then one down here, and we're still left with 2 over x. That's not bad. Okay, so that's not too bad. Let's have a look here. Let's see. Oh, what if, however, be very careful here. What if you have a derivative dy over dx when y is equal to, watch out, ln of x squared. Now, most of you might be thinking, well, I think that's just like y is going to be ln squared of x squared, and then I just find, wait, what? That's not even, first of all, that's not even possible. You don't distribute the squared to ln of, and then the x. You can't do that. You think in the distributed property, but that's, remember, the natural log is sort of like an operation. It's like saying minus x squared squared. It's like saying that the squared goes to x squared, and then the squared goes to the negative sign. Not you, that math doesn't work that way, and then it won't work out like this either. That's so squaring the natural log. That's an operation. You're taking the natural log. You're taking the log with the base of e of x squared. So you don't square the actual operation. The same thing here. A subtraction or negative, right? If you're subtracting x squared, you don't square the minus part. That's weird. Okay, that's an operation. So this is really tricky. I would normally give this to you in class to try to figure out, but really you don't have ln of u, do you? If you think about it, ln of u, you don't have that. It looks like ln of u, but then it's being squared. That's really weird. Okay. So let's see. What do we have? We have something that is being squared that is also differentiable. Let's take a look at our formulas here. What does it look like? Do we have anything that looks like that actually? No, because this is a constant. Oh, okay. So if it doesn't follow anything out here, doesn't really follow that. Doesn't follow anything like here. It doesn't follow anything like this, because I was thinking this, the derivative of a dx, but a has to be a constant. This is not really a constant. Well, let's just treat this as a chain rule. So this one, it does not follow any of the technical exponential and logarithmic functions yet for the first step. The first step is there, it's u squared. And let's see, we have to take derivative of y with respect to u. If you have to take the derivative of, let's see if y was equal to u squared, right? Yeah, I take the derivative of y with respect to u, so it'd be dy with respect to u. So sorry. If you had y is equal to u squared and dy with respect to u, it's simple. You just do du times du with respect to x. So I'm sorry. So if you take the derivative of y, but you're trying to find it with respect to x, okay, you take the derivative of u, which is, I'm sorry, it would just be the derivative of this guy would be 2u times, and you have to do so that's the derivative of the outside function. This can be differentiated, so you have to take the derivative of the inside function. 2u times du over dx. That's kind of what we have here going on right now. Because if you think about it, u is this guy, right? U is being squared. So this is what you're going to learn as u substitution. So I don't know. I think I'm getting ahead of myself here, but this outside function is being squared. Okay. And then you could take the derivative of the inside function. So it's the derivative of the outside function, which is going to be 2 times u times the derivative of the inside function, which we do know follows this thing. So this is multi-layered. This is very difficult. So let's define a few things. U is going to be equal, in this case, our ln is going to be whatever's in here squared. U is going to be ln of x. Now, what is the derivative of u with respect to x? Now we do this thing, ln of x. So the derivative of the natural log of something would be, we'd follow this, 1 over whatever is, so this is going to be a little confusing for you guys, so I do apologize. It'd be 1 over whatever's in here. So the derivative of ln of u, in this case u is x, is going to be equal to 1 over u. So that's going to be equal to 1 over whatever's in there, x, times the derivative whatever's in there with respect to x. Well, the derivative of this guy with respect to x is just 1, so it'd just technically be 1. So this would be 1 over x. That's it, du over dx. And then to make matters worse, right, we're going to plug all these into this ultimate guy here, which would be 2 times ln of x times 1 over x. 2 times u, ln of x, times du over dx, which is going to be 1 over x, we found out. So this is going to be equal to 2 times ln of x over x. I believe that is it. So rewind that a few times. I know that was super confusing, but essentially, let's go back. ln of x, I can take the derivative of ln of x using this guy here, right? Using this guy. But this squared is very deceptive. It looks really easy. It looks like the first example, but the first example is very different. The inside is x squared. So I could follow the natural log of this guy, and then it's just essentially 1 over u times whatever was on the inside, derivative of the inside. So it'd be like this. I would take this, I would just put 1 over u, which was 1 over x squared, times the derivative of the inside, x squared, which is equal to times 2x. That's simple for this one. This one, however, did not follow that. This is not this at first. This is a u statement or some guy that's being squared. So you have to find out the derivative of the big guy. That's really simple. The derivative of u squared would just be 2 times u, but it has to be you have to take into account that u is also differentiable. So it's the derivative of the u squared. It'd have to be 2 times u times whatever the derivative of u is. So it's very easy to define u as just ln of x, because again, u squared, what is u squared? U in this case is ln of x. So you say u is equal to ln of x. The derivative of u, the derivative of ln of x is going to be 1 over whatever was on the inside here times the derivative of whatever that guy it was on the bottom. So the derivative of ln of x is 1 over x, whatever the guy's in there, times the derivative of x itself, which is just 1. So it's just 1 over x. And I have to substitute all these guys back into here. 2 times u times du over dx. And I got du over dx is 1 over x. And then 2 times u is equal to ln of x. I said it that way. And I have this at the end. Remind that a few times to kind of go over that. It's actually, once you get the hang of it, it's not as bad as you think. But it's so hard to get through this because you're probably fumbling around with like, what? Wait, what does he mean? What's going? What? I hate this. Okay, so calculus is very much like that. Just come into tutoring, and then the more times I kind of go over it from different angles with you, and I can kind of describe it to you, I think it would just get stuck. So it's what I call the shotgun blast of teaching. I throw everything at you, and hopefully something sticks. Where it's just like, oh, I think I get it now. Okay, you just need a difference in perspective. Okay. Also, you could talk to another tutor as well, like anybody else, like a peer or something like that. Maybe they can kind of help out or work that out. Okay, here's an example for a derivative. One more example of log base a, say, x. And just to reiterate from your formula sheet, the original blue formula sheet, I'm just going to rewrite it out the top of the page, but here's this guy. Let's see, it's the derivative of x log of base a of u. So in this case, it's going to be more comprehensive than just saying x, but I'm going to make that a u just in case, like, because the derivative of x is just 1, but what if you get something in here that's not just x? It's like a 2x or 3x, you have to take the derivative of that too, the chain rule. So what the final thing is 1 over u times ln of a times du over dx. Okay. All right. So what's my problem or my example going to be? Let's try y is equal to log of 4x squared. All right. And then I want you to find dy over dx. What the heck is that going to be? Okay. Well, dy over dx is going to be equal to the derivative of log base 4 times x squared. Okay, so let's figure out a few things. let's use this general equation to define what, let's say, I don't know what my a is. A looks like it's 4. So this is step 1. Okay. Let's see, what else do I need? I need a u. So u looks like it's going to be x squared. This whole thing is going to be x squared. Then du over dx. What is the derivative of u with respect to x? That's going to be 2 times x. That's du, sorry, 2x. Okay. So now let's plug that in. So the derivative of this guy, the derivative of log over 4 over x squared, let's rewrite that as the log of, sorry, that would be 1 over u times ln of a. So my u would be x squared times my ln of a. So you're just going to write L times ln of a. A is 4. That's it. And then times du over dx. Du over dx is 2x. That's it. That's all you have to do. And that's going to be equal to dy over dx. Spend a few minutes pausing and looking at the notation there to see what you did. But that's it. That's all you had to do. Because it's just asking for the formula, the derivative formula. All right, guys. Hopefully that helps. Rewind this a few times to understand. And if it still doesn't click with you, come and see me and I can help you out. Okay. Thank you, guys. Bye.